So in this video we're going to be looking at discrete random variables. So a random variable is when we assign a number to each outcome in the sample space of a probability experiment. And when we're talking about discrete random variables, we're talking about where we have outcomes that are discrete data. So discrete data is data that usually takes only integer values, and it's often countable quantities. The number of times I roll a 6, the number of times I see a head when I toss a coin, the number of red cars that drive past, the number of females, whatever it might be. So it's usually a countable quantity, so you'll often be talking about the number of something. We'll talk more about continuous random variables in the next sort of chapter, which is more like measurable quantities: time, distance, height, weight, etc. So discrete countable quantities. And a discrete random variable is when we take a probability experiment where the outcomes are discrete values and we assign a numerical value, a discrete numerical value to each of those outcomes. So in terms of notation, a discrete random variable is usually defined using a capital letter, and then the specific values of that variable are referred to using the corresponding lowercase letter. So for example, if capital X is the variable which is the number shown when a fair die is rolled, okay, then lowercase x could take any of the values 1, 2, 3, 4, 5 or 6. So lowercase x is an element of the set of numbers that are 1, 2, 3, 4, 5 and 6. Okay, so lowercase x being the particular values of uppercase x, the variable which is the number shown when a fair die is rolled. Okay, so if we had another variable called h, the number of heads observed when a coin is tossed 5 times, well then lowercase h could take any of the values from 0 to 5. We could observe no heads, 1 head, 2 heads, 3 heads, 4 heads or 5 heads. If w is the variable, the number of wins a team has in an 8-week season, then lowercase w could take any of the values from 0 to 8. The team could have 0 to 8 wins out of the 8 matches they'll play in the season. D, if D was the number of days on which rain is observed in June, then lowercase d could be anything from 0 to 30. It could rain on no days in June, or it could rain on every single day in June. Okay. So then a discrete probability distribution is a listing of all of the possible values of the variable along with the corresponding value probabilities of each value, and we set that up as a little table. So for example, if we consider the situation where a fair coin is tossed 3 times, and we've looked at this example in previous videos, we're looking at probability problems, we've used tree diagrams and things like that to represent the problem. So the sample space of this experiment, and we could use a tree diagram to help us generate this sample space, is going to be head, 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 tail, head, tail, head, head, tail, tail, etc. Okay, 8 possible outcomes that could happen when we toss a coin 3 times. Each outcome is equally likely to occur, so each outcome has a probability of 1/8. For example, the probability of getting a head and then a tail is 1/8. So if we now take this situation and redefine it so that we have a discrete random variable, that is a variable that takes discrete numerical values. So then we reframe it as, let's let x be the number of heads observed in 3 tosses of a fair coin. You could equally let x be the number of tails observed. It's essentially going to give you the same thing. But we need to define it in a way that allows us to think about this numerically rather than with the outcomes being listed as HHT, for example. So if x is the number of heads observed in 3 tosses of a fair coin, then there are 4 possible values of x. So that is lowercase x is an element of 0, 1, 2 or 3. We could get no heads, 1 head, 2 heads or 3 heads. And so then we can set up the probability distribution as follows. So we have a table here that lists all the possible outcomes for x. Okay, so lowercase x, which is the specific values that uppercase x can take, can be 0, 1, 2 or 3. Okay, and then we list the corresponding probabilities. So if we get no heads, that's the one outcome which is tail, tail, tail. So there's 1 out of 8 equally likely outcomes that will give 0 heads. If we want 1 head, well, there's these 2 outcomes and this outcome, so 3 out of 8 outcomes, 1 head. Similarly, 3 out of 8 outcomes give 2 heads, and one outcome, gives 3 heads. Okay, so 1 out of 8, probability of 1/8. In terms of the notation we can use here, there are 2 alternative notations we can use in this spot. This is fairly common. We write the probability that uppercase X, remember uppercase X being the number of heads observed in 3 tosses of a fair coin, okay, that the number of heads observed is equal to lowercase x, which is the specific values. So the probability that the number of heads observed is equal to 0 is going to go here. The probability that the number of heads observed is equal to 1 goes here. The probability that the number of heads observed is equal to 2 goes here. Okay, so what we're seeing here, for example, what this number here tells us is the probability that the number of heads observed is equal to 2 is equal to 3/8. Okay. Alright, so now that the distribution is defined, so we should have every possible outcome listed here along with their probabilities, so that therefore means that the total probabilities must add up to 1 or we've missed an outcome. But now that our distribution is defined, we can easily calculate probabilities, such as the probability that at least 1 head is tossed. So that would be equivalent to saying the probability that x, the number of heads, is bigger than or equal to 1. Okay? And so we can see out of our possible outcomes, bigger than or equal, x being bigger than or equal to 1 is those 3 outcomes, probability that x equals 1, plus the probability that x equals 2, plus the probability that, that should be an uppercase x there, that x equals 3. So that is that probability, plus that probability, plus that probability, and so we have 7/8. Alternatively, actually it would have been much quicker in this instance, and anytime you find yourself adding up more than half of the probability distribution, it's probably easier to think about the converse, and that is to think about the fact that the probability that x is bigger than or equal to 1 is actually just going to be 1 minus the probability that x isn't bigger than or equal to 1. So in this case, that's the probability that x equals 0. So 1 minus 1/8 is 7/8. Either way, though, you get there. Okay, the distribution can also be graphed. So I've got the distribution here. Here's the alternative notation we can use to talk about the probability. This is probably less common, it's really just a space saver, but P of x can also refer to the probability of the x value up here. So it's the same distribution. We can graph it. When the x value is 0, the probability is 1/8. When the x value is 1, the probability is 3/8. When x value is 2, probability is also 3/8. And when x value is 3, the probability is 1/8. Technically speaking, the plot is just 4 dots, but we tend to, as we I was going to say as we've seen previously, but no, we'll see it in the future when we look at binomial distribution as well. But we can sometimes just add in these vertical lines just so that the 4 dots don't get lost on the plot, really. No more than that. But essentially, it is really just 4 points. Okay, probabilities of a discrete probability distribution. Properties of a discrete probability distribution. All the probabilities must be between 0 and 1 inclusive, so that's just a property of probability in general. So each probability has to be somewhere between 0 and 1. Obviously, we can't have a probability of 2.8, we can't have a negative probability, etc. And similarly, the sum of all the probabilities in the distribution must equal 1. And as I said earlier, if they don't equal 1, we've either made a mistake in working out the probabilities or we've left out a possible outcome. Okay, so given that information then, which of the following are probability distributions? Okay, so in part A, I'm not seeing anything immediately obviously wrong. So for example, all of those probabilities are between 0 and 1, so it meets that criteria. I now need to check that all the probabilities sum to 1. So 0.1 plus 0.2 is 0.3, plus 0.4 is 0.7, plus 0.1 only adds up to 0.9. Okay, so in this case, the total probabilities add up to 0.9, so we're missing an outcome there. So this one is not a probability distribution. Okay. Part B. Okay, there's no issue with the x values being negative. We don't know what the data is about. It's possible that we're measuring, I don't know, what something could be negative temperatures or let's say profit or loss, for example. We could have, if it's profit, we could have positive and negative values or whatever it might be. Okay, so there's no issues with the negatives there. All the probabilities are between 0 and 1. Let's check that they don't add up to more than or less than 1, that they add up exactly to 1. So 0.15 plus 0.65 is going to be 0.8. And then 0.12 plus 0.08 is 0.2, so 0.8 plus 0.2 is 1. Okay, so it does add up to 1. So this one is a probability distribution. Part C. That's an issue there. Okay, so this one's not a probability distribution. And D, I'm not seeing anything immediately wrong there. Let's have a think about what these add up to. A quarter plus a quarter is 2 quarters, which is a half. 3/8 plus 1/8 is 4/8, which is also a half, so they add up to 1. And so this one is a probability distribution. Okay. Alright, so let's have a look at an example here. The probability distribution of a discrete random variable y is shown below, so it's not always going to be x, so making sure we're using variables consistent with the question when we work with a problem. So this time the discrete random variable is y, we have the probability distribution shown here. So we want to find the value of A. So this is a fairly common question with discrete probability distributions. We've got an unknown probability, we want to find this value, so we know that all the probabilities have to add up to 1, and so we really just have to work out what A has to be, so they'll all add up to 1. So we're essentially saying that A is going to be 1 minus the sum of all the other probabilities. Oops, 0.17 plus 0.25. So it's 1 minus, so I just add those up, 0.02 plus 0.13 plus 0.38 plus 0.17 plus 0.25, so they add up to 0.95, and so therefore A must be 0.05. Okay, so we work that value out there. Find the probability that y is less than or equal to 3. Okay, so probability that y is less than or equal to 3 means adding up those 4 probabilities, or alternatively we could just add up those 2 probabilities and take them away from 1. Okay, so I'm going to do this as 1 minus the probability that y equals 4 plus the probability that y equals 5. Okay, so that is 1 minus. Now remember, we've just worked out A is probability that y equals 4 is 0.05, so 0.05 plus 0.25 is 0.3, so it's 1 minus 0.3, which is 0.7. So easier to add those up and take them away from 1 rather than add up those 4 numbers, so it's about efficiency. C, find the probability that y is bigger than 1 but less than or equal to 4. Okay, so bigger than 1 doesn't include 1, less than or equal to 4, so we're talking about those 3 probabilities there, so that's probability that y equals 2 plus the probability that y equals 3 plus the probability that y equals 4, and so that is 0.38 plus 0.17 plus 0.05, 0.38 plus 0.17 plus 0.05. Now obviously you should be able to add those decimals in your head as well, however you want to go about doing it. 0.17 plus 0.05 is 0.22, and then 0.22 plus 0.38 is 0.6, or whichever way around you want to do it. Okay, find the probability that y is greater than or equal to 4 given that y is greater than 1. Okay, so it's a conditional probability, so we know how conditional probability works. It's the intersection of those two things. Y has to be greater than or equal to 4 and y has to be greater than 1 over the denominator, which is y greater than 1. So intersection of those two things, 1, 2, 3, 4. Okay, if y has to be greater than or equal to 4, but also greater than 1, the intersection is just greater than or equal to 4. Okay, so you need to better think through those intersections. Alright, so this is the probability that y is greater than or equal to 4 over the probability that y is greater than 1. Sometimes you might have worked out one or two, both of those probabilities in previous questions, so always checking back to see if you've got those numbers, but we haven't actually worked out either of those. So I'm going to greater than or equal to 4 is these ones here, which is 0.05 plus 0.25, so that's 0.3. And then greater than 1 is the same as greater than or equal to 2, so that is all of those. Or we could think about it as 1 minus that, so they add up to 0.15, and so 1 minus that is 0.85. Okay, so it's 0.3 out of 0.85 If we're leaving our answer exactly, or we're working a tech-free paper, that's 30 over 85, and then 5 goes into both of those. That is 6 over, 5, I think it's, I'm doing 17, 5 17s, 50 plus 35, yep, okay. But if you're asked to give a rounded answer, although we're not here, so we're going to leave it nice and exactly. Let's see what the CAS gives us, 0.3 divided by 0.85. See, that's not going to round nicely. So you do need to be able to, even if you have got your CAS here, it's not going to give you a nice exact answer if you do 0.3 divided by 0.85. So having tools that enable you to work out, well, 0.3 divided by 0.85 is 30 divided by 85, and then you can get your CAS to simplify it that way. Okay, so unless you're told to give a rounded answer, don't give a rounded answer. And then part E, we want the probability that y is less than or equal to 4, given that y is greater than 1. Okay, so again, we need the intersection of those two things, y less than or equal to 4 and bigger than 1, over the denominator, which is y is bigger than 1. Okay, so again, thinking about 4, you know, if y has to be less than or equal to 4 and greater than 1, the intersection is this bit in here, which is going to be probability that 1 is less than y, which is less than or equal to 4. And we have worked that out in part C already, over the probability that y is bigger than 1. Okay, so our answer to part C was 0.6 over, we've already worked out y bigger than 1 in the previous question, 0.85. And so again, that's 60 over 85, which is going to be twice as big as this, so 12 over 17. Okay, example 3. A spinner is divided into 5 equal sectors numbered 1 to 5. The pointer is spun twice, and the number of the the sum of the two numbers is recorded. Set up a probability distribution for x, where x is the sum of the two numbers spun on the spinner. Okay, so we need to be able to think about what are the possible values of x, and this is where actually working with discrete random variables requires you to use the skills of general probability that we've reviewed in the last couple of videos. So tree diagrams, tables, all those sorts of things that are going to allow you to work out what are the probabilities that go into my probability distribution. So in this case, I'm thinking I would use a table here just to think about, and I don't mean a probability distribution table, I mean a table like this to think about the possible options. Okay, so I'm just going to double that one up. So, alright, so if we spin the spinner twice, and it could be the numbers 1 to 5. Let's say this is our first spin. Doesn't really matter which we nominate as first and second. Alright, and in our second spin we could also get 1, 2, 3, 4, 5. Okay. And then we sum the two numbers when we spin twice. So if we get a 1 and a 1, we're going to get, the sum will be 2. If we get a 1 and a 2, the sum will be 3, etc. And so we fill out the table with the sums, so we can see what's happening. 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 6, 7, 8, 9, 10. Okay, so set up a probability distribution for x. So x is the sum of the two numbers spun on the spinner. So we can see really clearly here now what the outcomes for x are. X could be anything from 2 all the way up to 10. Okay, so I'm just actually going to make all that a bit smaller. Sorry. I'm going to need a reasonably big probability distribution to show 0 to 10. 2 to 10. Alright, so we're going to have let's have x and p of x, or we can write probability that x equals x here. Okay. Alright, I'm going to have 9 different outcomes. 1, 2, 3, 4, 5, 6. Oh. I didn't quite get there, sorry. Go a bit thinner. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we could get 2, 3, 4, 5, 6, 7, 8, 9, or 10 as our sums. And then we need the probability of each of those things. So we can see these from our table. So there's one way of getting 2 out of 25 possible, one way of getting a sum of 2 out of the 25 possible spins that could happen. So that is going to be 1 out of 25. Probability of 3, that's 2 out of 25. 4, that's 3 out of 25. 5 is 4 out of 25. 6, you guessed it, is 5 out of 25, which will be 1/5. 7 is 4 out of 25. 8 is 3 out of 25. 9 is 2 out of 25. And 10 is 1 out of 25. Okay, so there's our probability distribution. And now that we've got the distribution set up, we want to find the probability that x is bigger than 4. And so that would be from 5 to 10, or I'm going to do 1 minus the probability that x equals 2. Sorry. I've actually covered up my undo buttons with my CAS. Just let me minimize that slightly. There we go. X is bigger than or equal to 2, plus the probability that x equals 2, or x equals 3, or x equals 4. So it is 1 minus, we've got 1/25 plus 2/25. Oops. 2/25 plus 3/25. So all up there we've got 1 minus 6/25, which is 19/25. Now once again though, you've also got the table here. So in terms of finding probabilities, you can refer to your probability distribution, or you can refer to your table, which is actually much easier in this case. The probability that x is bigger than 4 is going to be all of those outcomes. Okay, so we can count them up as 19, or again we can count up the 6 that aren't included and take them away from 25. So again, some flexibility about how you're going to work out your probabilities. You've got more than enough information to do it here. Probability that x is bigger than 4, given that x is less than or equal to 6. Oh, sorry, still got my highlighter there. So the intersection of those two things is going to be x is between, x is bigger than 4 and less than 6, so it's between 4 and 6, not inclusive of 4, but inclusive of 6, over x is less than or equal to 6. Alright, so between 4 and 6, but not including 4, is actually just 5 and 6. So we can see that's going to be, and actually sometimes it's easier, although we should always give answers in simplest form, it's easier for me to think about that as being 5/25 in terms of adding up the probabilities. And so it's 9/25 for the numerator, over the denominator will be, so we've got 9/25 divided by probability that x is less than or equal to 6 is all of those, and so we can add those up. Again, think about it as 5/25, so we've got 1 plus 2 plus 3, which is 6, plus 4, which is 10, plus 5, which is 15 out of 25. Okay, and again, actually easier to stick with the common denominator because they're going to cancel out when you're dividing fractions. So it's 9/25 times 25 over 15, and so actually it's 9/15, which 3 is a common factor, is 3/5. Okay. Again though, as I said before, you could use your table rather than the probability distribution. So if given that x is less than or equal to 6, so given that we are less than or equal to 6, so we're talking about all of those outcomes there. Okay. What is the probability that we are bigger than 4? Well, out of those, bigger than 4 is those. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 15. Okay. So again, being flexible about where you take your information from. Okay, final example here. Alex gambles on the roll of 2 dice. After the dice are rolled, the numbers that appear uppermost are added. The prizes are as follows. So he gets $0 if the sum is 7, $2 if the sum is even, $5 if the sum is 5 or 9, and $6 if the sum is 3 or 11. Find the probability distribution of x if x represents the prize money. Okay, so x isn't about the sum, x is about the prize money. So there are only 4 possible values for x. So X could be either $0, $2, $5, or $6. Okay, so in terms of our probability distribution, probability that X equals X, we just have 4 possibilities, 0, 2, 5, and 6, but we need to work out the probabilities of each of those. So again, thinking through a sort of table for rolling a die twice, or rolling 2 dice, equivalent probabilities, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, again it's about the sum, so filling out the sums, and I know this is a bit tedious, but it's ultimately the most accurate way to go about doing it. You might be able to work it or think it through without actually writing in the sums, and just sort of thinking through which cells in your table are relevant, but I find it helps you be able to see what's going on. Okay, so how do we earn a prize of $0? That happens if the sum is 7, okay, and we can see that that is there. There's 6 out of 36 outcomes with a sum of 7, so that's a probability of 1/6. Okay, $2 if the sum is even. Okay, so even, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 out of 36 is indeed half. Be careful about assuming that even will be half. Just, you need to be sure that you've got an equal number of odd and even outcomes to make that assumption. So, sorry, I deleted something here. So that was 1/6. This is half. Probability of getting $2. We win a prize of $5 if the sum is 5 or 9. Okay, so 5 or 9. So that's a total of 8 outcomes out of 36. Okay, which is going to be 2/9. And then $6 if the sum is 3 or 11. So 3 or 11, that is 4 outcomes out of 36, which is 1/9. Okay, we should check that our probabilities add up to 1 just to be sure. So what's our common denominator here? 18ths. So that's 3/18, that's 9/18, that's 4/18, and that is 2/18. 3 plus 9 is 12, plus 4 is 16, plus 2 is 18, so 18/18. Good. Okay, Alex pays $2 for each roll of the dice. So this is what he would win, but he has to pay $2 to play. Okay, find the probability that Alex makes a profit. So if he pays $2 to play, but earns a prize of $0, well then he's actually lost $2 in terms of his net gain. If he pays $2 to play and wins a prize of $2, he got his money back, but he hasn't actually made a profit. So he's only going to make a profit if he wins $5 or $6. Okay, so the probability of getting a profit is equivalent to the probability that X equals 5 or X equals 6. So that is 2/9 plus 1/9, which is 3/9, which is 1/3. So here's a 1/3 probability of making a profit. So it's not too bad again. Find the probability that Alex does not make a loss. Okay, so this might sound like the same question. My apologies. Might sound like the same question. But this is going to also incorporate the break-even. So he only makes a loss if he wins a prize of $0. If he gets a prize of $2, well, he's made his money back, so he hasn't lost anything. So no loss is if he gets $2, $5, or $6, which is equivalent to saying 1 minus the probability that he gets a prize of $0. He'll only make a loss if that's the situation. So it's 1 minus 1/6. So 5/6. So 5/6 probability that you won't make any loss. So actually, it is a reasonable game to play. In fact, it's quite a good game to play. Set up a probability distribution for Y if Y represents Alex's profit. Okay, so X is the prize money, but if he pays $2 to play, we want a different distribution for Y, which is profit. Okay, so the probabilities are going to remain the same, and there are still 4 outcomes, but we need to think about what that means for profit. Okay, so if he won a prize of $0, then his profit would actually be negative $2. If he won a prize of $2 and he paid $2, then his profit is 0. If he won a prize of $5 but he paid $2 to play, then his profit is only $3. And if he won a prize of $6 but he paid $2 to play, then his profit is $4. Okay, the probabilities still remain the same because this is still what happens when he earns a prize of $0. Okay, so your probabilities remain the same. So it's going to be still 1/6, 1/2, 2/9, and 1/9. Okay, but we're reframing the situation to now think about profit rather than winning. Okay, so the practice for today is from exercise 13C.